Namaste. Welcome to this channel Dr.ARM's Chemistry. Friends, we were discussing the stereochemistry, the part of this chemistry of 3D elements. And last time we have seen what is stereochemistry and what are the structural isomers, isomerism and geometrical isomerism. We have seen first point, that is first type of isomerism, that is ionization isomerism in the last lecture, and last part of that isomerism is remaining missed, we can see. So that is reactions, means how the isomers are prepared. For example, if you see some examples, so you can see the first reaction like this: CO Br2, when it is treated with ammonium bromide NH4Br, and in ammonia with oxygen also, then it gives the complex CO NH3 H2O and Br3. So the complex formation takes place in this way, and now when it is heated, it gives CO NH3 Br and Br2. This or further treatment with Ag2SO4, it gives CO NH3 SO NH3 Br, and this Br2 is replaced here by SO4. So this way we get one type of that is isomer. Similarly, if we consider second reaction, in order to prepare another isomer, we get CO NH3 Br, and here Br2 in ionization sphere. When it is treated with concentrated H2SO4, it gives CO NH3 and here it is HSO4. So this on treatment with sodium barium bromide Br2, it shows the replacement of this, giving CO NH3 SO4, and here it is Br. So here you will find that this isomer and this isomer, these are differentiated with respect to this position Br in coordination sphere. Here and it is sulfate ion in coordination sphere. Here sulfate ion is in the ionization sphere and Br in the ionization sphere. So in this way we can prepare the isomers. Hydration. Isomerism. In this type of isomerism, the water molecule, that is a ligand, is exchanged between the coordination sphere and the ionization sphere. So this gives us two isomers, and this can be prepared in this way. For example, if we take this and CrCl3 Cr Cl3 6 H2O. So this can be prepared in this way. CrO3, if we take the oxide of chromium, that is CrO3, this is a hot solution, and if it is treated with concentrated HCl, it gives the chloride CrCl3 6 H2O. So this is green crystalline. Green crystals are obtained, or you can say here green crystals. So when these green crystals are dissolved in water, it gives its hydroxide complex in this way. CrH2O 5 Cl and here Cl2 with water of crystallization, that is H2O, and this is blue green color complex. This is further converted into this CrH2O6 Cl3. It is violet. So here you will find that the water ligand, that is crystal, here it is water of crystallization, but it can be coming inside, and the Cl minus is going outside the coordination sphere. So you can remember these two complex forms which are different in color, blue, green and violet, and these are representing the hydration isomerism. Here we can confirm the presence of this Cl and this Cl by carrying out the test of the aqueous solution of these complexes with silver nitrate solution. The presence of chloride gives us white precipitate of AgCl. Then we can have some other examples of these cases. For example, this COCl EN2 H2O, and in ionization sphere there is Cl. This is one isomer, and its other isomer is Cl2 En2, and the ionization sphere contains Cl and this water of crystallization. So this water of crystallization ligand here moves out in the ionization sphere. So this water molecule is present in the coordination sphere. It moves into ionization sphere. Whereas one of these Cl moves here inside this coordination sphere. There is interchange between water molecules from coordination sphere and ionization sphere. Then this is about the hydration isomerism. Now we will go to the next type of isomerism, that is linkage and coordination isomerism. So the next isomerism is third, coordination isomerism. So here you will find that the complex is in the form of, means the coordination compounds contain cations and anions, which are both complex in nature. Means cation is neutralized by anion, and in this case both cations and anions are in complex form, and there is exchange between the two. Means metal ion is, we can say, found in different environments, but the ligands are same. Metal ion is different. So you will observe in the form of some examples. For example, if we consider this CO NH3 6, CONH3 this is cation, and now the anion is Cr CN6. So this is CONH3 3 plus, CrNH3 3 plus, and this is one compound of the complex species. The isomerism, so this is one isomer. Another isomer after the exchange of ligands is like this. So Cr, or we can say these NH3 are moving here, CN6 are moving here. So we get the complex species like this Cr, NH3 6. So this is cation, and its anion is CO CN6 3 minus. So this is another isomer. In this way we can have other examples. So we can have the examples. So this is one example we can see. Another example is like this: CO NH3 6 3 plus, and this is neutralized with CO NO2 6, and so this is one isomer. It's another isomer is CO NO2, that is partially CO NH3 4 NO2 twice, and another is CO NH3 2 NO2 4. Means here metal ion is same, but the ligands are exchanged within these. So here there are 6 NH3 ligands, 6 NO2 ligands in this isomer, but here few ligands of ammonia are moving here in this case. So you will find that there are out of 6 only 4 ligands of ammonia, and 2 ligands are taken from the 6 NO2. So 2 ligands of NO2, and here remaining 4 ligands of NO2 and 2 ligands of NH3. Similarly, you can have another example using platinum complexes. If we take platinum in 4th oxidation state, it is having coordination number 4. So if it is platinum NH34 and its anion part is platinum 4, also 4 with Cl6. So this is one isomer, and its another isomer is platinum with a different oxidation state. That is, here it is 4. It is 4, having NH3 4 and Cl2. NH3 4 and Cl2, and there is another part is platinum 2 with Cl4. Platinum 2 with Cl4. So in this case also you will find that the Cl ions are exchanged as a result of which this platinum 4 here it is converted into this means oxidation state is same. Here it is platinum 4, so here it is platinum 2, but the required electronic charge is balanced here by using appropriate number of Cl minus, etc. Then we will have another isomer, that is linkage isomer. Fourth isomer is linkage isomerism. In this case, you will find that the ligands are in the complex, in any given complex, the ligands are same, but the point of attachment, means coordinating point of attachment of the ligand is different. Means such ligands having 2 or more coordinating points of attachments or donor atoms, we can say. These are called ambidentate ligands, and when such ligands are present in the complexes, the isomers are obtained by using the same ligand with different points of attachments. For example, if we consider the thiocyanate ligand, that is SCN, so sometimes the point of attachment is nitrogen and sometimes the point of attachment is sulfur. So on that basis, we can consider the thiocyanate in different environment. Similarly, if we consider another ligand, that is NO2, sometimes the point of attachment is nitrogen and sometimes point of attachment is one of that oxygen. So in this way, these ligands are called ambidentate ligands. Ambidentate means there is possibility of 2 points of attachments with which the ligands are coordinated with metal ion. Now, if we consider the example like this, CO NH3 here NCS, here nitrogen is point of attachment 2+, and another isomer is CO NH3 and it is NCS also with another point of attachment, that is sulfur. So here the ligands are same, molecular formulas are same in both cases, but these are the 2 examples, means 2 compounds are just having difference with respect to the points of attachments, and that is why there is difference regarding the linkage between the metal ion and the ligand, and therefore they are called these linkage isomers, and this phenomenon is called linkage isomerism. Now we will see the preparation of such complexes of isomers. Now, if you see the CO NH3 Cl2, when it is treated with dilute aqueous ammonia, it gives the complex CO NH3 H2O, here it is H2O and Cl2A ionization sphere. Now this went treated with NaNO2 in concentrated HCl. It gives the replacement of water molecule by NO2, giving this complex CO, NH3 5 NO2. Here nitrogen is this point of attachment. You see it's showing different color, that is yellow color. This further the reaction takes place spontaneously in warm HCl or UV reaction, spontaneous reaction, which shows change in the coordination point, that is giving this CO NH3 5 NO2 with oxygen as a point of attachment. The underline indicates the donor atom. So this is showing that it is red in color. So distinction can be done on the basis of color. Another is yellow in color. Now the IR absorption takes place at different frequencies. Here metal oxygen, the nitrogen oxygen mate. So this, in this case, this oxygen metal stretching vibration appears at 1065 and 1470 per centimeter. Whereas in this case the metal nitrogen bond shows characteristics vibrations at vibrational band, we can say at 1310 and 1430 per centimeter. So in both cases the IR absorption shows distinction. In case of metal oxygen bond, the stretching vibrations are appearing at 1065 and 1475, whereas in case of the metal nitrogen bond, the stretching vibrations are appearing at 1310 and 1430 per centimeter. So we can confirm these isomers on the basis of some simple tests or using instrumental methods of analysis, that is IR absorption or infrared spectroscopy. So this is about the linkage isomerism. Now in this case we can have another example where we can have the DMSO linkage. DMSO means in some compounds the dimethyl sulfoxide is used. So if we consider DMSO, dimethyl sulfoxide, dimethyl sulfoxide, that is DMSO. So it can coordinate using sulfur and oxygen. Sulfur and oxygen are coordinating atoms. Coordinating atoms means these are donor atoms. So using these different donor atoms, we can have some examples. Now, the ion absorption spectroscopy can also show the distinction between these sulfoxide with different points of attachment, that is S or O. So for example, nu bar for sulfoxide for DMSO, dimethyl sulfoxide, is 1055 per centimeter. So here the sulfur oxygen stretching vibrations are observed at this case, at this region, that is S bonded DMSO. Here for S bonded DMSO, this is for free. Now for S bonded DMSO, for S bonded DMSO, thus vibrations, higher vibrations appear at 1080 to 1150 per centimeter, and for O bonded, oxygen bonded DMSO, the vibrations are appearing at 890 to 950 per centimeter. So these values will explain the distinction between the sulfur bonded and oxygen bonded DMSOs. The structure of this DMSO is like this. Structure of DMSO is like this. So you can say this is sulfur and it is bonded to this oxygen, and these are the three CH3 hydrogen, like this. So we will see the structure of such DMSO ligands, structure of complexes containing such DMSO ligands. Now, if we take the examples of complexes containing ruthenium, then you will find that, say, this is ruthenium. It is bonded with chlorides like this, and here remaining ligands are Ne2, OS, Ne2, OS, and here SO, Ne2. Similarly, we have this SO, Ne2, and another SO, Ne2. So this, after undergoing change in presence of heat or UV or any electromagnetic radiations. So it undergoes interconversion, giving us another complex that is ruthenium. Here you will find that Cl is replaced by this SOMe2. This Cl is as it is. Another Me2OS. Then there is this Cl SOMe2. Here it is OS, oxygen bonded, and here it is sulfur bonded, SOMe2. So you will have difference shown in this way. So you can observe this O bonded and this S bonded. These are S bonded ligands. So we can use such type of suitable example. So with this we have completed the structural isomerism, and in the next lecture we will go to see what about the stereoisomerism using the distereo isomers, that is the geometrical and optical isomerism. So and we'll go to the next point in the next lecture. Till then, goodbye, see you next time. Please subscribe to this channel, please press the bell icon and like button also. So thank you very much.